Alright, so we were looking at bibliographic and co-citation coupling last time, and I said there's a very similar approach we will do for what is called this bipartite graph analysis. Okay, so first of all, what a bipartite graph is. This graph I show in the middle is a bipartite graph. So in a bipartite graph, as you can see, there are two partitions of vertices, and all the edges in the graph are between the two partitions. Okay. Now, all the vertices could be kind of similar type. For example, all of them could be like the users of a social network or employees in an organization and so on. They could be also of two types like this. So that's why I indicate here one set of vertices with integers 1, 2, 3 and so on, and the other set with alphabet A, B, C, D. So this is a typical use of bipartite graph where you have affiliations involving the vertices. So this could be, say, the employees of an organization, and this could be, say, the different divisions within the organization. So one employee may belong to only one division, or an employee could be part of two divisions. Or this could be the actors in movies, and this could be the movies in which they have acted. So some actors could have acted in more than one movie and so on. Now, what we could be interested in is what is called the vertex projection and group projection of these vertices. Now, what I mean by vertex projection is, so we'll call these vertices with more, this set of vertices with more vertices as the vertices, and this we can call as a group. Okay, so the affiliation is a group. So in the vertex projection, what we want is, we want just a network of the vertices such that two vertices are connected if they have at least one common group between them. So for example, 1 and 2 are both affiliated to group A, so we can have an edge between them. 1 and 5, they don't have a common group. So 1 is affiliated to just A, 5 is affiliated to B, C and D. So they don't have a common group between them. So there's no edge between 1 and 5. So that's the way you build the vertex projection graph. Okay. So you have an edge between two vertices, they have at least one common group between them. Now, we can also similarly get a group projection graph such that there's an edge between two groups if at least one vertex is affiliated to both of them. So A and B, they have at least two, vertex 2 affiliated to both A and B. Whereas A and C, they don't have any common vertex. So A is having 1, 2 and 3 affiliated with it, whereas C is having 4 and 5 affiliated with it. So there's no common vertex affiliated to both A and C. So there cannot be an edge between A and C. So this is how you can build a group projection graph. Now you may be asking, do we have to do it manually? No. So that's what we are going to see a procedure to do to get this projection graphs. Okay. So it's similar to the co-citation bibliographic coupling approach using matrices. Now, the matrix that we are going to build may not be a square matrix because we are dealing with groups and set of vertices. So both need not be of the same size. So typically, the smaller set of vertices, we will follow the convention of calling that as the group, and the vertices that the set that has more vertices we'll just call as the vertex set. Okay, just for our convention. So we'll have the rows as the groups and the columns as the vertices. So I think it's the same graph I have here. A is affiliated to 1. No, it's a different graph. Okay, so let us use this graph now to build this matrix and do the analysis. Okay, so this is again a bipartite graph. So again, the key thing in a bipartite graph is all the edges are between the two partitions. No edge is between vertices in the same partition. Okay, so we have the groups represented in the rows and the vertices in columns. So an entry is a 1 if that vertex is affiliated with that group. So 1 is affiliated to A, so the entry for A1 or 1A is a 1. 2 is not affiliated with A, so the entry for A and 2 is 0. Similarly, 3 is not affiliated with A, so A3 is also 0. But 4 is affiliated with A, so it is A4 is 1. 5 is not affiliated to A, so A5 is 0. So this is how you build this adjacency matrix. It's not a need not be a square matrix like in this case, but we will still call it as adjacency matrix. Now see, same thing, like B is not affiliated with 1, so there's no it's 0, the entry is 0. B has affiliations is 2, 3 and 4, 2, 3 and 5, so the entries are 1, and with 4 there's no edge between B and 4, so it is 0. So that is how we build the adjacency matrix. So once we build the adjacency matrix, we can do what is called as vertex projection and group projection. So let us do the vertex projection first. So vertex projection means we want to build this such a graph involving only the vertices. Alright, so there are 5 vertices. So you want a network of 5 vertices. That's what you want to build. So we are considering any 2 vertices I and j, and we have to decide whether there could be an edge between I and j or not. So we are considering all the groups. So here I indicate k to be the variable from 1 to g. So g is the number of groups, and this B is this adjacency matrix. So an entry bki is a 1 if k and I have an edge between them. So in the sense that if vertex I has an affiliation with group k, then this entry bki is going to be 1. If I is not affiliated with group k, then it is 0. Similarly, bkj is going to be a 1 if vertex j is affiliated with group k, otherwise it is 0. So if I and j need to have at least one group in common between them, this product has to be 1 across, at least 1 considering all the groups k equals 1 to g, right? So if both I and j are not affiliated with a particular group k, then the product for that particular k is going to be 0. So if I and j are affiliated with the same group idk, then then 1 times 1 is going to be 1, and consider all such possible groups k from 1 to g. So similar to what we did in the coupling problem, we cannot multiply 2 matrices with their what you call the column in ID is different from the row, or the column index is different from the row index. So we have to do some adjustment. So one thing that we can do is this k is a common index. So to bring this common index or make the common index match, we can do it like this. Take the transpose of the first matrix, so that becomes then ik matrix. So the k is now the column index, it matches with the row index here. So now we can do matrix multiplication as the transpose of the adjacency matrix times the adjacency matrix itself. So that's what I show here. So we write the transpose of the adjacency matrix. You all know how to do the transpose, so just invert the rows and columns. So this row becomes a column. 1 0 0 1 0, that is a row, is now the column 1 0 0 1 0. Now 0 1 1 0 1 is now the column. Then 1 1 1 1 0 is now the column. Then 0 0 1 1 1 is the column. So that's the transpose. Multiply it with this matrix itself. So this is a 5 row 4 column matrix. Multiply with a 4 row 5 column matrix. So a 5 row 4 column matrix multiply with a 4 row 5 column matrix, the product is going to be a 5 by 5 matrix. So that corresponds to the 5 vertices we have. So the product matrix is going to be a square matrix. Okay. So it's 5 rows and 5 columns. So what do the entries in this matrix indicate? So basically for any two vertices, it's going to capture the number of common groups they are affiliated with, because you see in the product what we are doing, the product will be a 1 if both I and j are affiliated with the group K. So how many such groups that we can have so that the product is a 1 and we add them up all, and that will be the number of common groups to which both I and j are affiliated. So let us do that. So again, for matrix multiplication, we can do things in parallel. That means we don't need to really do anything sequential to compute this matrix. We can just pick any cell in random and just compute that particular cell, and you can do that in parallel for every cell. So let us pick, say, 3, 4, row 3 and column 4. So I want to compute this number. So that means you're picking row 3 and column 4 means pick row 3 in the first matrix and column 4 in the second matrix and do the pairwise multiplication addition. So it's going to be 0 times 1 plus 1 times 0, which is still 0, and then 1 times 1 plus 1 times 1. So that is going to be 2. So that's how we get this 2. If you want to do something else, say row 2, column 5, means row 2 in the first matrix, column 5 in the second matrix. 0 times 0 plus 1 times 1, that is 1, and then 1 times 0, then 0 times 1. So we have only 1, so that's entry is 1. And the diagonal basically is like a vertex with itself. So let us do row 3, column 3. So row 3, column 3 is like 0 times 0 plus 1 times 1 plus 1 times 1 plus 1 times 1. That is 3. So as I said, these entries indicate the number of common groups, and you can cross check. So we got 3 and 4 as 2. So look at 3 and 4. 3 is affiliated with B, C and D. 4 is affiliated to C, A, C and D. So C and D are the two common groups to which both 3 and 4 are affiliated. So that's why we have number 2. 2 and 5, 2 is affiliated to B and C, whereas 5 is affiliated to B and D. So B is a common group to which both 2 and 4 are affiliated. So the diagonal then would basically indicate the number of groups to which a particular vertex is affiliated with. So for 3, vertex 3, we have 3 because vertex 3 is affiliated with 3 groups. It's like 3 and 3. What are the common groups? That's the same as telling the number of groups that a particular vertex is associated with. Vertex 2 is affiliated with 2 groups, that's why you have 2 in the diagonal. Vertex 1 again has 2 groups affiliated with it, so it's 2 groups. So that's how you get the vertex projection matrix. Okay, and it's also what you call a symmetric matrix because it's like undirected and the vertices are affiliated to other vertices. So if 2 and 5 are affiliated with each or to some group, it's the same as telling 5 and 2 are affiliated with that group. Okay, so that means the row 2 1 1 2 0 is going to be same as a column 2 1 1 1 2 0 with respect to vertex 1. Similarly, with respect to vertex 2 1 2 2 1 1 is same as 1 2 2 1 1 for vertex 2. 1 2 3 2 2 is same as 1 2 3 2 2 for vertex 3. So this is another way you can cross check whether you got a symmetric matrix or not, to check for any math error. So that is vertex projection. Using a similar approach, we can get a group projection. So group projection, what we want to do is we want to build a graph of just the groups. So here we have 4 groups A, B, C, D, and we want to build a graph of these 4 groups. So again, we want to now consider here the vertices that are affiliated with 2 groups. So 2 groups I and J are going to have an edge between them if there's at least one common vertex that is affiliated to both I and J. So that is why here in the summation I'm considering the K to be the vertices, so the vertex IDs. So K can go from 1 to n, and there is if K is affiliated to both I and J. So you see here the convention that we have is the group is the row. So that's why I indicate like here, the I and J are here the groups. So IK, the entry IK is the one in the matrix means there's the entry for row I, column K should be a 1. So the entry for row I, column K is a 1, then Bik is a 1. Then similarly, the entry for row j, column k is a 1, we say Bjk is a 1. So the product will be a 1 if both Bik and Bjk are 1. So that means there is some vertex k that is affiliated to both I and j. So again, we cannot multiply right away. We have to have the the column index of the first matrix match with the row index of the second matrix, and k is the common index. So we will keep the first matrix as it is, but transpose the second matrix and make it like Bkj when you do the transpose. So the column index matches now with the row index. Then you can multiply these two matrices. So to get the group projection, you will primarily do the matrix multiplied by its transpose. So we'll write the matrix as it is and multiply it with its transpose. So the transpose is again inverting the rows and columns. So the row is 1 0 0 1 0, that becomes the column. 0 1 1 0 1 is now 0 1 1 0 1, and 1 1 1 1 0 is this. So again, you can multiply and get any cell in this product matrix, which is also a square matrix and symmetric matrix. So let us see if you want to get BD. So again, here the rows are the group IDs. So row B entry for BD means row B in the first matrix and column D in the second matrix. So in the matrix B, adjacency matrix, the rows are the groups. When you transpose, the columns become the groups. So when you want to get an entry for BD, you are still multiplying based on the groups. So row B in the first matrix with column D in the second matrix. So that's going to be 0 times 0 plus 1 times 0 plus 1 times 0, so still 0. So 1 times 1, then 0 times 1 plus another 1 times 1, so it's 2. So BD, the entry is going to be 2. Let's do one more, say DC. That means row D in the first matrix with column C in the second matrix. That's going to be 0 times 1 plus 0 times 1 plus 1 times 1 plus 1 times 1 plus 1 times 0. So it's going to be 2. 1 times 1, 1 times 1, or 2 times, so that's 2. Again, the diagonal indicates the number of vertices that are affiliated with a group. So if you want to get, say, BB, that means row B in the first matrix, column B in the second matrix, that is 0 times 0 plus 1 times 1, that's a 1, plus 1 times 1, another 1, then 0 times 0 plus 1 times 1, so it's 3. So that's why we have 3s for the entry for BB. So that it basically indicates the number of vertices affiliated with group B, 2, 3 and 5. So that's group projection. Okay. So if there's no edge between two groups, that means they are not affiliated with, they don't have any common vertex between them. So for example, there's no edge between A and the entry for AB is a 0. So that means there's no common vertex between A and B. So you can check, A has 1 and 4 affiliated with it, whereas B has 2, 3 and 5 affiliated with it. So there's no common vertex. Any other group pairs, we have at least one common vertex between them. So with this idea, for example, if you have the actors and the actors as the vertices and the movies as the group, we can find out which two movies have no common actors between them, right? So if the groups or the movies, in this case A and B, so you see the entry for A and B is 0, so these two movies have no common actor between them. So that's something interesting to find out. Similarly, you could even do it for collaboration networks. So for example, this could be the the topics, the key topics or keywords in the papers, and this could be the actual papers. So there's an edge between a paper and a keyword if the paper mentions that keyword, okay, at least once. So if you want to find which two papers don't have any common keywords between them, then you could do a similar analysis and find out what papers have no common keywords between them and so on, right? So I have some examples of bipartite graphs. So one thing we talked about is actor-movie network, and they are in biological area. So there's something called the disease sum network. That's basically a network of the diseases and the genes associated with them. So it depends. I think the genes may be larger in number compared to the diseases. So diseases could be the groups and genes could be the vertices, and using that genes disease network, so which genes are kind of associated with the diseases, that's what the network will capture. So if some mutation means some changes in a gene may cause a disease. So that's how you build a graph of the diseases and genes, and then you can get some group projection like this, and the entries like this will indicate which two diseases have no common genes associated with them. Then this matrix will indicate how many diseases are associated with two genes. So for example, you can say there's no disease. You see, the mutations a disease might occur if the mutations occur in two or more genes or just in one gene. Okay, depends on the disease and the genes. So, but an entries like again 0 for two genes 1 and 5 indicate that these two genes are kind of not related, or they don't together cause any disease. Okay, so if you do some diagnosis and find out there's a mutation in one particular gene, you can pretty much be sure that gene 5 will not be activated due to that mutation in gene 1. Okay, and things like that. So you can do some analysis using this vertex projection, group projection like this. Any question on this? So it's a very important, interesting and useful approach. Alright, so let me just save this.